Deflection of beams. The deformation of a beam is usually expressed in terms of its deflection from its original unloaded position. The deflection is measured from the original neutral surface of the beam to the neutral surface of the deformed beam. The configuration assumed by the deformed neutral surface is known as the elastic curve of the beam. So we have here a simply supported beam, a hinge and a ruler. It's a varying load, and in this case we have the elastic curve, which is the deformed shape, the dotted line, and the maximum deflection is at this point, and the deflection is designated as y, and at a distance x. Because the design of beams is frequently governed by rigidity rather than strength, for example, building codes specify limits on deflections as well as stresses. Excessive deflection of a beam not only is visually disturbing but also may cause damage to other parts of the building. For this reason, building codes limit the maximum deflection of a beam to about 1 over 360th of its spans. And we have the analytical methods for determining the deflections of beams are method of double integration. The primary advantage of the double integration method is that it produces the equation for the deflection everywhere along the beams. Number 2, moment area method. It is a semi-graphical procedure that utilizes the properties of the area under the bending moment diagram. It is the quickest way to compute the deflection at a specific location if the bending moment diagram has a simple shape. And method of superposition, in which the applied loading is represented as a series of simple loads for which deflection formulas are available. Then the desired deflection is computed by adding the contributions of the component loads, or the principle of superposition. Simply supported beam with uniform load, and we have a simply supported hinge and a ruler, and a uniform load W from left support up to right support with a distance L. And in this diagram, we have the maximum deflection. The formula for deflection or maximum deflection is equal to 5WL to the fourth all over 384 EI. So this will be used if the load is uniform. So we have here the beam deflection formulas for simply supported beam. So we have load case. We have a concentrated load P at the center of the beam, which is L over 2 at the right and L over 2 at the left support. And the maximum deflection is equal to PL cubed all over 48 EI. Another load case, we have a concentrated load P, and at a distance A from the left support, and at B or distance B at right support. And the deflection or maximum deflection is equal to PB open parenthesis 3L squared minus 4B squared close parenthesis all over 48 EI. Another case, we have the uniform load of a simply supported beam, and as we discussed, we have the deflection maximum is equal to 5WL exponent 4 all over 384 EI. And the next load case is a triangular load, and we have a distance L, and the maximum deflection is at X, and the formula for maximum deflection is equal to 0.00652 WL exponent 4 all over EI. And another triangular load, The maximum deflection is at the center of the beam, and the formula, it is equal to WL exponent 4 all over 120 EI. And the last load case, we have a moment at the ruler, which is a moment M, and the maximum deflection is located at x distance from the left support. And the formula for maximum deflection is equal to ml squared all over 9 square root of 3 EI. Example number 1. An 8 by 12 wood beam with E is equal to 1,600,000 psi is used to carry a total uniformly distributed load of 10,000 pounds on a simple span of 16 feet and I equal to 950 inch exponent 4. Find the maximum deflection. So we have a uniform load of 10,000 pounds, or the total uniformly distributed load of 10,000 pounds, and with a length of 16 feet, and I, which is 950 inch exponent 4, given. We have the dimension of the beam, which is 8 by 12, so 8 by 12 size of the beam. Then E, or modulus of elasticity, E, which is 1,600,000 psi, and a uniformly distributed load total, which is W, big W, which is 10,000 pounds, and a span or length L, which is 16 feet, with I, and it is equal to 950 inch exponent 4. Then you need to find the maximum deflection. So this should be maximum. And the formula for a uniformly distributed with a simply supported beam for deflection maximum, we have maximum, and the formula, we have 5W L cubed all over 384 EI, and we have W, which is 10,000 pounds, so 5 times 10,000 pounds, and we multiply with the length, which is 16 feet, then we convert 16 feet to inches, so 1 foot is equal to 12 inches, and we divide by 1 foot, and close parenthesis, cube, cancel out foot, and then we divide with 384 times E, which is 1,600,000 psi, and I, which is 950 inch exponent 4. So we compute 5 times 10,000 pounds times 16, open close parenthesis, is 16 times 12, and then exponent cube, and then we divide by 384. Also we divide by 1,600,000 and 950. The maximum deflection is equal to 0.61 inch. So this will be the maximum deflection of a uniformly loaded distributed load of 10,000 pounds with a length 16 feet. Example number 2. Consider a simple wooden bench with legs 1.5 meters apart from each other at their centers. Let us say we have a 4 centimeter thick and a 30 centimeter wide eastern white pine plank that act as the seat for this bench. Eastern white pine has a modulus of elasticity of 6,800 megapascal. Let's suppose that a 400 Newton child sits in the middle of the bench. Determine the maximum beam deflection. So we have here a simply supported beam with a length L, which is 1.5 meters, and a force P, which is 400 Newton, the weight of the child, and seated at the middle of the bench. And we need to compute the maximum beam deflection given. So given, we have the length L, which is 1.5 meters. Then we have the base, which is 30 centimeter, and the thickness or the depth of the plank, which is 4 centimeter. The weight or the load of the child, which is P, 400 Newton. The modulus of elasticity of the eastern white pine, or E, is equal to 6,800 megapascal. Find the maximum deflection of the beam or the bench. So this would be maximum deflection solution. First, we need to determine the value for moment of inertia, which is I. And we're using a plank, which means it is a rectangular beam. And we have the base and the depth. And the formula for a rectangular for moment of inertia, we have b d cubed all over 12. And then we substitute the value for b and d. B is 30 centimeter, and we multiply by the depth, which is 4 centimeter and cube. And then we divide by 12. The value for I is equal to 160 centimeter exponent 4. And then we convert into meter. So 1 meter is equivalent to 100 centimeter and exponent 4. So the value for I in terms of meter exponent 4, you have 1.6 times 10 to the power negative 6. And the unit is meter exponent 4. So we have now the value for I. And then the maximum deflection of a concentrated load at the center of the beam, we have the formula, which is PL cubed all over 48 EI. Then substitute the values. P, we have 400 Newton multiplied by the length of the bench, which is 1.5 meter, and cube. We divide by 48, the constant, and the value for E for an eastern white pine, which is 6,800, and we multiply by times 10 to the power 6, which is Pascal. And we multiplied by the value of I, which is 1.6 times 10 to the power negative 6, and it is in meter to the fourth. The value for the maximum deflection is
400 times 1.5 cubed divided by 48 times 6,800 times 10 to the power 6 and multiplied by 1.6 times 10 to the power negative 6. And this one, we can cancel out 10 negative 6 and 10 exponent 6. And the value for the deflection maximum, it is equivalent to 0.00258 meters, and we equate to millimeter, and it is equivalent to 2.58 millimeter.